The broadcast is now starting. All attendees are in listen-only mode.
Welcome everybody to this last meeting of BCS SPA of 2020. Quite a different year than we expected when we started out. I'm very pleased tonight that Rob Chatley has introduced me to Giuliano Casale, who is going to talk to us about the RADON framework and how to do serverless computing with rational decomposition. I'd love to tell you what's going to be in our first meeting in January, and unfortunately I can't, because nobody's been lined up for that yet. But I'm sure we'll find something. Maybe one of you has got a very good suggestion as to what the theme should be. But you'll find out via the usual mail groups. And I'm going to get out of the way now and let Giuliano give his presentation. Thank you very much, Giuliano.
Thank you very much, Immo, for the kind introduction, and thanks everyone for attending this presentation. It's a great pleasure for me to be able to present the work we are doing as part of the RADON project, which is a European Commission-funded research project aimed at building an open source framework to create applications based on microservices and also based on serverless computing technologies like function as a service. I'm going to present first the agenda of this talk. I'm going first to review with you some basics about function as a service in particular, and also some very quick concepts on microservices, but then I'm gonna move to presenting RADON, why we think this is a solution that can help software engineers in building applications based on functions as a service technologies. And then I will discuss with you the models that we use to describe serverless architectures, which are based on the OASIS TOSCA standard. But the models we have built in this project actually extend the standard. So I will then briefly discuss the RADON TOSCA models, which allow you to essentially describe the architecture of a microservices and serverless-based application in such a way that the model can drive the deployment and configuration of the application. And this is the main difference from the OASIS TOSCA standard, which does not support natively function as a service. And then, depending on time, we will see some materials concerning quality assurance. Let me get started then with my talk. So I like, first of all, to say a few words about this project. This is a fairly large initiative. It's a 4 million euros project funded over 30 months that involves the organizations you see in this slide. There are several universities, Imperial College London, Tilburg University, University of Stuttgart, and University of Tartu, as well as a number of companies, ATC in Greece, Xlab in Slovenia, Pragma in Denmark and Norway, and Engineering, which is a multinational based in Italy. And the idea of this project is to offer a DevOps framework to help, in particular, the European software industry adopting serverless fast technology in their products, trying to minimize code and data lock-in. So I will explain these notions in more details in the next slides, but let me just show you the faces of the people involved in this project. We are a group of around 40 researchers. Most of them are junior researchers, like PhD students, but we have also some senior people, and I am the person here highlighted in the top row. And so let's just spend a few words for a brief recap on some essential notions here. So when we look at the progress of software technology over the last decades, it has been clearly very sharp. Cloud computing has changed a lot. And so we have moved from a scenario where applications were typically monoliths to the introduction of web services and service-oriented architectures, which, however, came before cloud computing and cloud programmability. So certain aspects of automation or auto-scaling that we see today with microservices were not yet present with service-oriented architecture. So microservices bring this idea of decomposing the software architecture to a new level where different teams can manage different microservices, and serverless platforms build on top of this idea by offering even finer grained decomposition. You can essentially decompose at function level the software architecture, but also operate these functions in the cloud with really minimal need for operations teams or demanding configurations when you run these functions in the cloud. Every good software engineer, after some experience, can get very familiar with deploying and running a serverless-based application in the cloud. And clearly, as I'm sure most of you are aware, serverless computing has been a mega trend in the last few years. You see here the cover of Communication in the ACM, the international organization of computer scientists that acknowledge the rise of serverless computing over the last few years. It has been really interesting for many ways due to its simplicity. First of all, it's very easy, as I said, to run this function in the cloud, but there are also the reasons, for example, related to cost. If you serve a function from the cloud, it might take very little to serve a call from a function, even a few milliseconds. And this means that you might be billed actually just for the execution of this business logic, and not for the period, or at least not significantly for the period where the function is, or your service in general is idle. In particular, when you look at the billing of the functions, there is a roundup coming up from the fact that you're going to be billed to a minimum. But if you compare this situation with the one of a virtual machine that stays idle for hours, if not days, of course, the costs are on a different scale. And the function as a service has found a lot of uses, but one that is particularly important is, for example, in IoT, where you can have edge devices which trigger events. And what happens when you process an event with a serverless function is that through an event gateway, the event will trigger the execution of functions which are containerized on the cloud platform that serves the call. So either the function is already in memory, in which case it will process the event and return the results in external storage, because there is an assumption that these functions are stateless, or otherwise the function will be retrieved from a code store and the runtime initialized, and so you will have some latency before the function is loaded in memory, is able to execute the event, which is often called the cold start of the function. So there is some performance degradation upon using these functions compared to a VM or a traditional service, but once the function is loaded, you don't suffer these cold start latencies anymore. And there have been anyway many improvements, particularly in the last year, in terms of performance of public cloud platforms. Now, serverless function as a service is, for this reason, very interesting and important, but from the point of view of software engineers, it also carries a number of interesting questions on how we should design the applications, because the fact that these functions are stateless means on the one hand that we can be more relaxed in terms of performance management, because for the platform it will be way easier to auto-scale these functions. But on the other hand, the fact that the state change needs to be continuously persisted on storage, and the different resources in the environment where the function runs can generate events that trigger the execution of the function. So you might have events from the edge of the environment. You may also have that if you deposit, say, an image in a bucket, that action in the technical infrastructure triggers the execution of a function. And therefore, you have a rich space of events, and therefore you have the problem of harmonizing different technologies, harmonizing different type of events, so that you can run a coherent architecture and also exploit the richness of this environment. And this clearly calls for novel software engineering methods. Now, what companies are seeing this? Well, in addition to the points I mentioned already, many developers see value in quickly prototyping with fast cloud-based applications, because you can build demos using your library of built-in functions even in hours. As I said, you have cost reduction, and these are natural to combine the paradigm with microservices-based architecture, for instance, thanks to auto-scaling and ability to redeploy automatically through CI/CD the code. So it's very much consistent with the paradigm. There are many use cases, too many to list in any slide of serverless FAS. Just to mention a few, in addition to IoT, you have uses in terms of batch processing, even data analytics, even though the idea that you move data to the code, to the function, is possibly an anti-pattern for performance. The fact that the functions are simple to use has spawned a range of use cases where people don't care too much about performance and just send the data to the function for processing in complex workflows. Or ETL, extract, transform, load data processing, can also be done effectively to functions. So there are many, many use cases. And so you might wonder why we offer to in RADON to develop a framework to build the serverless application. Can't you just take a commercial offering and use that, right? Why building a framework to help you doing this? Well, there are scenarios, particular vertical domains, where it is very important to have a degree of abstraction in the way you design your system compared to the case where you invest everything in a particular technology. I'd like to make an example that came up in an interesting conversation with a company we were talking to in the space of microgrids, which are essentially technologies in the broader space of smart grids, whereby you find in rural communities like in Africa or in South America, electricity generation through renewables, and you want to have a cyber physical system, in particular a combination of the physical infrastructure like the electric inverters and the IT infrastructure to do diagnostic and prognostics of the state of these infrastructure, as well as management of the electrical loads. You want them to run together, and you also want to add progressively more and more community on the go to this platform, right? So there is a lot of investment in technologies to help this kind of developments in Africa, South America, Asia, and several other regions. And service computing is seen as a way to process efficiently these workloads. Imagine you have a fault or reliability issue in an inverter. You can have a function that pulls the data from the edge and analyzes the condition that triggered that faulty situation. And so in terms of requirements from this story, we have that you need to be able to connect different technical architectures, integrate them with these, expand this backend that does the management. You also want to understand the topology carefully because it's a highly decentralized system. So you want to have a kind of a graph to understand which resources are at the edge, which are in the cloud backend, and reason about the architecture in a simple way. And of course, costs are important because this is meant to help rural communities. So you want cheap solutions where possible. And so some of the major requirements are therefore the ability to account for heterogeneity, multiple technology environments, for example, supporting multiple target cloud platforms, including hosted solutions, not necessarily only public cloud, and have low-cost event-driven processing. Now, with these premises, RADON comes in with the idea of offering a model-based approach to this problem. So we offer a collection of modeling primitives that you can use to specify your architecture, creating models that are actually deployable. And so they're not like, say, UML models, primarily documentation, I would say, for the architecture, but they're actually artifacts that you can use for concrete deployment of the architecture and update on a continuous basis. And these models and the environment surrounding the models supports different target clouds, public and private, as well as mixing in the architecture, stream processing, storage component, databases, traditional VMs, so you can have heterogeneity. And you can see in this example a more sophisticated topology than the one of the previous slide, where you see a fairly complicated set of relationships between functions running on AWS and storing, as you see here at the bottom of the topology, the results on a bucket. So the functions are all these vertically stacked elements. And you see they run on AWS in Europe. And so this is an example of a kind of a function level topology that you can define with RADON, and we will see some videos about this. Before we get there, just a few words on what we offer in terms of tangible outputs. Our framework consists primarily of an IDE based on Eclipse Che, which is an online version of Eclipse. It's not as complex or rich as the classical Eclipse, but is supported by the Eclipse Foundation. And this IDE comes with the graphical modeling tool, which produces the models you've seen in the previous slide, as well as a set of quality assurance tools, which I will mention later in my presentation. We also have a number of tools for runtime execution that deal with CI/CD, orchestration, so creating, starting, stopping the components of the application, monitoring, and a function hub repository where you can store your application logic. You can also have a template library if you use our stack in order to store the different functions that you create so that they can be reused. And there are also prototypes of scripts and recipes to deploy and configure functions over the supported platform. So these come already provided by the project. This is, by the way, a completely open source project, so everything is available on GitHub, but I will say more about this later. You see a screenshot of the Eclipse Che environment, which runs in the browser. And And there are various workspaces that you can instantiate, essentially mapping to the different type of projects that you can create, and you will find also a RADON workspace if you download our solutions. This framework at a bird's eye view consists of the components I mentioned before, which are essentially in the relation you see here, the tools, particularly those in green, are integrated plugins to the IDE. I will expand particularly on these three you see here: the graphical modeling tool, the decomposition tool, which allows to decompose a monolith into microservices, and the continuous testing tool that is for load testing. But there are also other developments which I will mention more briefly in my presentation. And after you design your application and the code in the IDE, the business logic, you can pack everything and ship it to the orchestrator for material deployment and configuration. So, as I said, our solution is based on OASIS TOSCA, and I want to give you some information about this standard. I know you have had other webinars on solutions like, for example, Terraform. So this is related paradigm, but a competitor in the end. Is a model-driven approach to cloud-based automation that has been standardized by OASIS now since a number of years. It is particularly popular in the telco industry, I will say, where it is extensively used even by well-known commercial operators as a way to abstract the resource management, for example, when you need to orchestrate network functions. And this is a completely portable and interoperable standard. Now, the essential elements of the TOSCA standards are the description of the application topology and later the orchestration of this topology. So before we get into some definitions, just a look and feel of how a TOSCA model appears. You see it is a YAML-based model. There is also a possibility to use other formats like XML, but in the latest incarnations, YAML has become way more popular. And you see in this particular example that the components, for example, here at row 26, these lambda functions are mapped to types which qualify their nature, as well as to a collection of properties that are not simply labels or textual descriptions to explain what this function is, but they're really the piece of information that will be used during deployment and orchestration to bring up and down the function in the runtime environment. For example, you have a mapping to the artifact that implements that function. And so in terms of the definitions in these TOSCA models, you have these nodes that represent the components of your application: web server, VM, your application, say, written in PHP. And you can have also the PHP runtime, the infrastructure like EC2, and various relationship templates, which are these connections that describe the dependency types between these components. And they're called not templates and relationship templates because they are essentially a descriptor of what the real instance will be once the orchestrator will create the system. So these types qualify, of course, the kind of node you are creating. The relationship typically are two types. Hosted on is a placement relationship, like the VM runs on EC2. You see here in dashed on top left another type of relationship, which is a software dependency, like dependence on a runtime or a library call. These properties already mentioned describe the characteristics important for lifecycle management of these components. But let me add that these properties are not static information. They can actually be instantiated at runtime. So you can, for example, bind an order to an IP at runtime, or have the orchestrator annotate the weights of a load balancer directly in the node properties. There is also the possibility to specify the requirements for certain nodes and capabilities offered by other nodes that allow to verify that the pairings you describe with the relationships are correct. In addition to these logical dependencies, it is possible to map these nodes to concrete artifacts for the deployment, so the concrete implementations, for example, of your application, as well as binding to these node templates, essentially artifacts that describe the implementation of particular actions defined in interfaces of these nodes, which the orchestrator will recognize as supported operations. For example, installation, configuration. So all these lifecycle management operations are also described in the standard, and what you can do is to associate an implementation artifact to that particular stage of the life cycle, so that the orchestrator will know what to do in order to accomplish that stage of the life cycle management. And holistically, these architectures are stored into so-called CSAR files, Cloud Service Archives, that bundle the model, the definition of the node types and relationship types, as well as all the artifacts I mentioned. And so depending on how much you pack, you might call, for example, a service template everything except the files and deployment plan that you might want to attach to the service specification. If you also exclude certain details about the node type definitions, you might call it topology templates, but in essence, this is a collection of these elements that ultimately is passed in this XAR archive to the orchestrator. This is just a zip file containing all these materials. And so this is our file, as you see, has these artifacts, the type definitions, the node templates and the relationship templates, as well as possibly some information that in particular orchestrators derives the order in which the activities are carried out upon deployment. And so a Tosca compliant orchestrator will receive this CSAR file and start to orchestrate in order the creation and configuration of these nodes in the cloud. So starting from these kind of templates, the orchestrator might either retrieve the plan stored in the CSAR or generate its own custom plan, and therefore start to provision the nodes taking into account their order of dependence until the application goes live. So I hope these notions are clear. I will move now to the graphical modeling. So what is the difference between the RADON models and the standard Tosca models? Well, the difference, as I said, is that you can have also...
I have a question for you.
Sure.
You've given a very clear indication of what RADON and Tosca are doing for us. Have you any comparison with existing other frameworks, such as particularly Terraform, Garden, things like Pivotal Cloud Foundry, and also the
that's
Cloud Formation, which is provided by AWS. What's the advantage of this?
One advantage certainly is that this is a vendor-neutral solution, and therefore you're not bound to a particular technology stack by a certain provider, but you can use it to orchestrate applications on different targets. So this covers part of the cases you have mentioned. But also from our point of view, in terms of this being a research project, we have certain well-defined semantics in this model that is used to reconstruct in memory all the dependencies in a non-ambiguous way that are used later by our scientific tools for processing. Also, because it's standard-based, you have essentially a significant community of both multinationals and SMEs that continue to develop, and I would say also together with academia, continue to develop this standard. So if you are a smaller company and you want to have your say on certain extensions, so there are open working groups. So I would say that it's gaining traction, particularly to this non-commercial and vendor-neutral aspect. But also let me perhaps add that compared to several of the solutions you have mentioned, it has had Tosca strong uptake in the telco industry. Really major operators that many use in Europe for mobile phones have in their orchestration stack Tosca, so it's picked up quite a lot. It's very much mature for I don't know, configuring firewalls, configuring network functions, voice over IP, etc., etc. So for this reason, it's been adopted very widely in that industry, and now progressively is also expanding more to the broader software industry. So I make no claim that it's indispensable to use this particular approach, but certainly is a very open and community-driven solution.
Thanks very much.
Thank you for the very interesting discussion point. Also, in terms of differences compared to the standard, RADON models allow to specify events, because one big shift here is that we're moving from a declarative approach for the topology of your application to having to specify the way the functions call each other, and so you have a set of behavioral dependencies, right? And so you need to also being able to describe this in the Tosca models, bound the call of a function to particular events, so a novel type of relationships. In particular, we use the cloud events open standard to create these relationships. Also, some functions can be scheduled, not just called on demand, and so you need to distinguish between these two cases. And also we have added extensions to describe the movement of the data, because if you use these functions to process, we said you need to store the data in the outside the container, so you need also to describe the data pipelines, right? So it gets way broader, the space of entities you need to play with when you enter in this domain. And so we have done all these extensions, and we are part of the standardization group of Tosca, so we are also pushing our work in the standard, but standardization typically takes some years to finalize the augmentation standards. So you see here the example of what you can do in RADON that you cannot do with Tosca. We have already seen this notion. You can add components like, in addition to specify the target platform, the function, or buckets, and link them to events. You see this relationship as a RADON data types.event that binds to an S3 event object created. So these are very simple thumbnail generation system that picks the event of object creation in S3 for the image, and then realizes that the image needs to activate the thumbnail generation function. And so now, as we've shown before, Graphical aids help, because you might have tens of functions and many tens of relationships. So it's good to have graphical approach, and our approach is based on this graphical modeling tool, which is an extension of a tool developed by University of Stuttgart, who is a member of our consortium. This tool is called Eclipse Winery. It's an official Eclipse project. You can download it also outside the context of RADON, all open source, and we have extended though to use our RADON Tosca extensions. And so you see some screenshots, but we will have later some videos. And so actually we have immediately the first video I want to show, which gives you a look and feel of the environment from instantiation of a workspace to actual deployment. And so what I'm going to do is also to give you some basic information about what you need to do to install this Eclipse Che environment. We offer our own SaaS version, but you might also decide to install your own Che, and you can still use our work. So let's see together this video, which I recorded quite recently. So in this video, you see we are at the GitHub page of RADON. We have all our repos, but it is particularly important, this RADON methodology repo, because it brings you to a directory. You find here the coordinates on trying RADON. There is a form to fill if you want to play with what I'm showing in this presentation today. There's a list also of the characteristics of the different tools, how to, videos or how to get started. I point to the IDE in particular. In this line, the dev file is really what you need to customize Eclipse Che in order to use our tools. So now we are in a live Che instance that we offer for these trials and also for our development. So we're logging in and we are presented with this currently empty set of workspaces. So what we can do is to essentially create a new workspace. And so we click now on add workspace, and we are presented with this dial window where we specify our new workspace, and we paste here the dev file we have copied from GitHub. This gives the instructions to Che on where to retrieve from GitHub all of our tools. And so this runs on Kubernetes, this environment. So when we click create, it's gonna create all the containers with our tools automatically. And you see it's a web-based IDE. And now you are inside this RADON environment. And so it is taking some time to instantiate everything. The video in this part is accelerated. In reality, will take some minutes to create all these containers. I show you here the creation of an empty file just to see that this is a standard web-based IDE. We will actually use later this file. And so this is the standard Eclipse Che, but if you click on the right, you can access the list of our tools, and we are clicking now on this Winery graphical modeling tool. So we go in Winery. These are projects that we saved with various service topologies. We go on this serverless to-do list project. which is simply a to-do list hosted in the cloud. And so you find some description at the beginning, but you go to the topology template, and if you click on Open Editor, you're brought into this graphical environment. So it takes a little bit to load, but you see now that our topology is showing up. There are 5 functions of type AWS Lambda function hosted on this AWS platform. You see that we specified there the region is the Frankfurt region, EU Central 1. And there is also the API gateway element, which maps to the AWS API gateway service, as well as a DynamoDB table component, which also maps to DynamoDB, of course. And when we click on the functions, you see that you can bind to list handler. List is the name of the function, so the actual object is called list. The function is a list.js, and then there are various configurations in terms of timeouts, memory, and all the characteristics of these functions. Now, if you click on the relationship, you can also see that when you call on the gateway /todos, it's gonna run a get on that function, so we can link the gateway and the function in that way. If we go back to our initial winery panel, we can export the CSR I've been talking to in our ID. So you see there the application has been bundled, the code was already available, and then it has been actually pulled from the function repository. And now we click on deploy. There is some authorization. Here we have a remote SaaS that accepts the credentials of the ID if it's properly configured. We have, for example, our new project in this remote SaaS. So this SaaS, just to be clear, is the remote orchestrator. So we have a SaaS solution that receives the CSR files and orchestrates them on our behalf. And so we created the project that will, we will run in this orchestrator, and then we ask to deploy. Before let's have a look to this project inside now the environment of this remote SaaS orchestrator. So I had pre-configured the credentials on this SaaS environment, and now we are ready to deploy. So the credentials at the AWS key, and so we have to specify the Tosca file that we want to deploy in our CSR. At the moment, this is done manually, but we expect to make this a bit more automatic in the future. There is a possibility to supply to the orchestrator additional parameters to a YAML file, which was empty in our case. And now we have launched the deployment, and we see in the remote orchestrator that the deployment is in progress. And so now the orchestrator has received the CSR and is calling all the various AWS services to bring up the functions, DynamoDB, and the API gateway. So there is first an ACK that the operation is pending. So from the ID, you would see that this has been committed successfully to the orchestrator. As usual, it takes some minutes before AWS brings up everything, so you can keep there refreshing. You can also check the log files, but if you have, for example, the dashboard open, you can patiently check the situation there with the deployment for the API gateway and for the functions. At the moment, there is nothing yet, but progressively you see that the functions start to show up in our panel. And so there were 5, if you remember. Now we are at 3. We need to wait a little bit more, and they will eventually show up all. You see that we are in the Frankfurt region as requested. Here is the 4th, and so now we will get the missing one. And so this has been, some waiting time has been cut. In reality, it takes a bit more minutes. And so now all the functions are live. We are waiting for the API gateway to come up as well. And so this is the screen you see until there is something actually running. So in a couple of seconds, we will see that by refreshing both screens, the API gateway pulls up actually. So now we try to refresh, and we see indeed that has picked up the serverless to-do list. And so if you click there, you are now presented the possibility to test these APIs. So if we run, for example, a get, we can check that our functions have been shipped with the code we expect. So if you click on test, you launch this get on the to-dos endpoint, and you see that we have received the have coffee to do and the other information that were available at the beginning in this to-do list. Okay, so this completes this video demo and shows you essentially end-to-end the minimal use of the framework. Okay. Is there any question before I continue? Okay, so hopefully this will give you a way also to reproduce some of the steps easily. You've seen how to install the environment of RADON. So let me then move to the next slide. So in terms of support for multiple clouds, we have seen in this demo that in terms of a region, it's easy to change the region. If you want to move to from Frankfurt to another region, just change in the model, and it's way easier perhaps than doing manually in the dashboard. But also we have similar elements for Google Cloud Platform or OpenWhisk or OpenFAS if you want a hosted deployment, and so on-premise, sorry, deployment, and so it's easy to change the topology if you know what you want. Now, if you want to learn more about this graphical environment, in addition to our documentation, I will encourage you to look at the winery.readthedocs.io that explains how to install through Docker this environment on your machine if you want to play with these models without having to deal with the entire framework. But to get the serverless extensions, you will need RADON. In terms of what happened with the orchestrator, just to recap, the graphical modeling tool can either send to the orchestrator directly, as we've seen in the demo, but can also use CI/CD to talk to the remote orchestrator. It doesn't need to be necessarily the one I've shown in the presentation. And this orchestrator will bring up everything from the containers to the functions, but also the supporting services like the monitoring platform that is shipped by default with RADON. Actually, the workflow is a little bit more complicated because there is identity management. We have this TPS template library publishing system that allows an organization to maintain different templates of different functions and components, so you can store your business logic in this environment and retrieve it for using these models at a later stage. Okay, so this closes the first half of my presentation, which was about these essentials of modeling and deployment. And you find, by the way, more information about this on our project website, and we also have a YouTube channel with other examples. What I want to discuss from now on are tools that deal with quality of service in the context of this project, where we see that this formalization into the models helps because we can embed the research tools around these models in the same way that the research community has built for many decades, I would say, tools around models like UML, you have also a proliferation of interesting and novel tools around these deployment models. And so let me explore with you this more research-oriented dimension of the project. And so in the project, we have various tools. Three I like to mention first are the verification tool that deals with annotating through a language that we call constraint definition language, logical predicates to require certain behavior from your application. And verification can take annotated RADON TOSCA model and verify whether these conditions are meaningful, so the pre and post condition can be met or not. This is done statically, it's not done at runtime, so there may be some limitations. In particular, we look at the conditions that are visible from the topological structures, like the relationships, the reachability of one component from another component, and so forth. Then you have a defect prediction tool, which is essentially, I would say, a debugger, not for code, but for these deployment models. So there is a scarcity of this kind of tools around in the open source space. And so this is a tool that looks at the way you define these architectures and try to give you some indication whether there is something wrong or not, whether you left a password in clear or not, and so forth. And the continuous testing tool is primarily a load testing tool. So let me say a little bit more about each of these solutions. As I said, CDL, the constraint definition language, is a language that allows to express using particular logic the preconditions and post-conditions that qualify the correctness of the execution, for example, of a function. And what perhaps makes the language a little bit different from similar logic-based languages is that it has been defined to be able to predicate on the same entities and relationships that you see in this RADON TOSCA model. So you can directly name your components or software elements in the architecture using this logic-based language. And so here is an example where we have two buckets for uploading images, and you have also some geographical information about the position of these buckets in Europe. You see different data centers. And so you might have in the CDL model associated to this TOSCA model that you, for, I don't know, GDPR reasons or other kind of national policy, you might have constraints on the data that you can share with another country's geographical placement. And so you might say that if the data is in UK, it can be moved after processing by a function anywhere, but if it's created in the US, it must stay in the US, or similarly for China. And so you can express these facts using CDL, and then with the verification tool, you would take the model, take the logical constraints, and determine possible inconsistencies, because you see that a function might write to a bucket that is placed in the wrong nation. And so here is a screenshot of how this logic language looks like. It is actually Turing complete, so you can do everything that you like with it. And once you run the verification tool, you might be indicated that there are inconsistencies with the post condition. So you might have that you write to the wrong bucket. And so the tool is able not just to detect these bugs, but also propose modifications that could be in terms of changing the location of your buckets, or changing the post conditions themselves. You might even supply a partial specification of a model plus some examples of possible ways to complete this model and try to come up with suggested refactorings for your model to complete the missing specification. So from examples of concrete instances, you can get constraints that are a little bit more general. And this covers the verification part. When we move to the debugging, and as I said, this is called defect prediction in our tool chain. This is a tool that looks at the source code of the Ansible scripts that we use for deploying the application, as well as the Tosca models that have as attached artifacts these scripts. So essentially, you pass the Tosca model, you say that there are some Ansible scripts that do the configuration and deployment, and this tool is going to debug everything recursively, basically. This is a tool that calculates a number of features out of these models and code snippets, and tries to understand if there is something anomalous. And so you see inside the RADON IDE various features that are detected, even in terms of style, how many blank lines you have, deprecated keywords, modules. So it tries to come up with advice also on the quality of the way you essentially code these systems. And so there are many type of defects. So there are, it's not just yes, no answer. There are many type of defects and patterns that are supported, and there are many classifiers based on the latest techniques in machine learning. Think to regression methods or SVMs that allow to classify whether the features associated to these artifacts are suspicious enough to make you think that there are defects, and so you are flagged, and then you can look more in the details if that's an actual problem or not. Last, in terms of the load testing, I said that we have support in the tool chain. So generally, in load testing, of course, you want to stress the system by launching artificial workloads that bring the system typically in high load to check scalability, for example. So the system under test is exercising its ability to scale. And of course, when you have so many functions and so many components, you want to automate this process because it's complex enough even without a large architecture. If you have also that, you really need a DevOps type automation. And so this continuous testing tool gives this type of automation. Is a tool that is perfectly integrated with CI/CD and essentially runs automatically load tests on endpoints of your system. And so generally you can define test cases, you can execute them, and there is even life cycle for this test. And so everything is managed by this testing server that we call CTT, continuous testing tool. And so basically you have the application, you have a description of how the test needs to look like, and the infrastructure where to conduct the test. And these are actually annotated as well in the RADON models. And the CTT server can look at all this annotation and all this information and come up with information for deploying the test. So the orchestrator, in addition to receiving, Exopera is the orchestrator. So in addition to receiving the instruction to deploy the application, it also receives in this testing phase the instruction to deploy the testing infrastructure, basically. So all of this is containerized as well. And so the test will run automatically, workload will be randomized according to some distribution, and then you get test results back to the user, which will be analyzed and presented as a report. So you see, just as a screenshot, how the endpoint testing annotation looks like in Winery. So you can indicate the paths of the endpoint and require that this is an HTTP endpoint test, and this will make sure that all the information for the test are stored and then can be executed automatically. Now I want to talk about another bit of this work, which is the so-called decomposition and optimization work. So this is another tool that deals more with aspects related to performance of the architecture you have designed and granularity of the architecture. So generally, in terms of performance, what you want is that you want to meet certain scenarios with a certain response time for your functions. And what can happen is that you might not have enough memory or enough concurrency in the execution of those functions in the cloud that allows you to scale when the workload is large enough. So of course you will pay more if there is a larger amount of resources you request to the provider, so the provider needs to ask you how much you want to about that. So it is one of the few parameters that you are obliged to provide when you deploy these functions, unless you're happy with the default, of course. And so the question is how to optimize the allocation of these parameters for your needs, so that you meet the service level objectives, but also you incur minimal operating costs within those expectations on performance that you have. For what concerns the decomposition of the application, as you design the architecture, in addition to this performance and cost constraints, you might want at some point to migrate your monolith or even your bulky container that has many endpoints into a collection of functions. So how do we refactor an existing specification of these architectures into something based on functions and more fine-grained? And so these tools offers this capability. And so from the architectural point of view, the tool interacts with the IDE and offers services for decomposition and optimization at the moment. We expect in the next 6 months to add also enhancement of these models based on monitoring data. And now, in terms of the backend, there is a computational backend that runs an optimization program. It's based on MATLAB, but it's based on the MATLAB runtime environment, which is royalty-free, so there is no expectation that you have a MATLAB license. And so what happens in this model is that we have extended the Tosca models also with annotations to describe characteristics like the amount of requests you get per unit time, right? If you have a request every 2 seconds on average, you need to tell me, because otherwise I cannot evaluate your scalability if you don't tell me how many requests you expect to have. And so we added a notation for this. We add also a notation to require performance objectives, right? So say that a certain call to a function needs to take less than or equal to 2.5 seconds. And so in general, our objective with the optimization side of the tool is to allocate the values of memory and concurrency. And so what we have is that generally, if we go to a a lower level of description. You can see these as forming basically a workflow, and we will look at optimizing these parameters. So several variants of this model will be considered until finding one that matches the objectives, but is also hopefully as close as possible to global optimality. This depends also how long you're gonna wait for the optimizer to finish, because it's generally computationally difficult as a problem. And so the way it works behind the scenes is that these graph relationships and the propagation of the request in the call chain is mapped to a stochastic model called a layered queuing network, which describes the different entities and endpoints and resources like virtual cores or resources where your software layers are deployed on. And this is a mathematical formalism that allows to gather insights on the expected response times, throughput, utilizations, and all the performance metrics that you might want to predicate on as you design this architecture. And so there are solvers that are either based on simulation or on mathematical analysis that provide these predictions. And so you are able to get these recommendations of memory and parallelism by solving possibly thousands of these models automatically. And the user just sits and waits. So we will see now a video that illustrates how this feels like. So let me play this video. You see now a topology where there is, again, a fast application on AWS with buckets and AWS platform, but you see that there is this RN stands for RADON. This abstract node represents the abstract workload that you imagine for your application, so that we were specifying before the arrival rate of that workload. Now we are specifying the expected response time policy, which we ask to be for this policy less than 5-second response time. And it is possible to map this policy to different functions. So you see it's active, this response policy on this function and this other function. And so now the tool knows that that's what you want. And so you go on the Tosca model, you run the decomposition tool, which has this feature called optimization. So if you call optimization in that menu, the model is going to be sent to this MATLAB backend that runs essentially a genetic algorithm. It's a search technique that finds a minimum cost solution. And now it has returned back to the IDE the model that has the recommended memory level, 512 megabytes, and concurrency for the functions, so up to 41 functions. So what we might do, we might, of course, deploy this automatically with RADON, but we might also basically go to our AWS dashboard and adjust these parameters on our functions directly, the memory, and as we said, the concurrency. So you see here you have the panel for the concurrency is 1, the default value. You can reserve 41 parallel instances, and then you load test. So in this case, we are doing a manual load test just for the sake of illustration. So we use Locus, is a common DevOps tool, and so it's sending at the rate we asked in that abstract workload model requested to this function, and you see under the average in milliseconds, the average response time that is observed. We asked less than 5 seconds, and you see that at this rate it's staying around that level, is temporarily growing a little bit higher in the initial phase, but as we add actually more more resources. We carried out, so maybe let me stop this to explain. So in this first experiment, we had configured only the first of the two functions, right? So what we had done is that we were running the experiment with just that function receiving the memory and concurrency parallelism that we chose, and you see they violated the threshold. But then I cut from the video the part where we were also configuring the second function. And in this case, you see that when you holistically configure as the tool told you the functions, actually this latency that was 6 on average in the previous test now drops down at a way more reasonable level that meets the SLA. So this is not just a proof that we meet the SLA F5 second, but it's also a proof that if you ignore some of the instructions of the tool, you might actually violate that SLA. So we regard this as an illustration of correctness of the tool. So you see now that the response time is 3.6 seconds on average. Okay, so this completes, is going a little bit, but is staying at a constant rate. The RPS here is the response per second, so it gives you the throughput essentially of this test. So this concludes also this demo. And so let me move now to a demo of this other feature, the feature that relates to the decomposition in finer grained elements. So let's play this shorter video. What we see here is a containerized application which has several endpoints. You will see that initially is based on this container environment. There are several entries which are essentially entry points for the endpoints for your calls, and so what we ask, you saw before there was a property called fine-grained, is your model that you want to refactor to require this decomposition tool to perform a fine-grained decomposition. So it will take some time to reason. There is also a possibility to do clustered decomposition based on ontologies of similarity between different elements of your architecture. But in the example, we are basically breaking down this container into a collection of functions. So you see now that we have got a YAML file that has instead a lot of functions where before we didn't have those functions. If you load that refactored decomposed model, you see all these functions that before were only inside the container. So you don't need to redraw everything. It takes a lot of time in complex models. Is done everything automatically. Okay, so this concludes also this demo. So we are approaching the end of my presentation. So I've just a few more slides, which will nicely fit in the 10-15 minutes left, to describe some research that we conduct in the project that is not as, say, focused on the implementation, but is more about principles, right? As a research project, we are also interested to push the boundary in terms of what we do with this technology. So I want to give you a glimpse of this, but on our website, you will find also several publications and deliverables, which are essentially reports where we explain the work we have carried out, both on the technical and the research part. And so this particular example of our scientific research I want to bring up deals with the management of the resources that are allocated to microservices that you might instantiate with the RADON stack. So you can imagine you have your Docker architecture, And you might be faced the decision to scale a runtime adaptively your containers, either through horizontal scaling or through vertical scaling. If you use functions, everything is auto-scaled for you from the by the provider. But if you're using microservices, it might be that you want to use what say Kubernetes or whatever system for container management you use, but typically those policies are quite reactive in nature, they're quite simplistic. But it turns out that you can do better than that. You can use some proactive mechanism to scale, where you try to see the workload trends and you try to predict what's going to happen if you now try to rely on those predictions to auto-scale. And so you might build, and we have implemented a system around your microservices architecture, which is your Tosca architecture. You might have a system that continuously essentially collects monitoring data to estimate this called service demand. You see the system monitor provides in real time data that you like utilization, response times of the request and so forth, that lead to a quantification of the average resource consumption of your microservices, which is put together with the Tosca models that give you the architecture. And now you can generate, as before, these stochastic models to reason on what if scenarios. What if I increase the CPU share to the microservices versus to the other one that is on the same host? And so the controller runs these optimization programs every number of minutes, and then can adjust automatically these CPU shares on your behalf. And so you see here these layer queuing models again, which are derived by the Tosca model. But you see now that these parallelograms are essentially the microservices, and these smaller parallelograms in each of them are the endpoints. So here you have a microservice that acts as a front end to the home catalog and cards request. It's running on a certain CPU core or a certain environment. So the circle is just the placement on a particular virtual or physical resource. And what you see is that every such endpoint can be annotated with requirements of time extracted automatically from the monitoring data of the execution of that endpoint on the underpinning physical resources. So when you call cards, it will take some CPU time locally, and then will issue also calls to these other endpoints of this other microservice card service. And now the response time of these calls will include this resource consumption of get, add, and delete. So the compound response time will recursively aggregate everything that comes from these calls in terms of latency, but also take into account the queuing that occurs at the physical resources if you have multiple microservices that are running on these resources at the same time. And in terms of this demand estimation, that can, so the resource consumption estimates, they can come from utilization measurement, but that tends to be a kind of a noisy estimate. You don't reconstruct very nicely the resource consumption as nicely as if you collect, for example, min queue lengths, so essentially unfinished jobs that are currently running in the system. You check the response time of this of the job. So you say, I make a call to cards. In my system, there are 5 or 10 executing requests at that instant. And I see on the y-axis that my response time for that call is around 20 milliseconds. Now, if you plot all these pairs of the unfinished work and the response time observed for that call, it turns out that you can prove mathematically that there is a nearly linear relationship. I say nearly because there is random noise on top. And it is amazing how accurate this is, because these that you see here are actually numbers from the real system. You see that really, you see the linear trend that the mathematics would predict between this relationship, because you can, of course, relate how much time it takes to serve you to how much queue there is in front of you, right? So that's why you see a linear relation. And now with these demands and the predictions, we can not just scale the CPU share, but also, for example, decide whether we replicate a certain stateless service. And so our controller over time will be able, as the workload is increased, to scale the performance of the system. So what we are comparing in these graphs you see is for 3 different types of workloads that I'm not detailing here. These are workloads that essentially create a spike of requests after the first handful of seconds, and this persists for quite some time. What you see here is the reaction of 3 different control mechanisms. Atom is our mechanism based on these predictive models. In yellow and orange, you see a reactive horizontal or vertical scaler. So what changes with using these models is that because the models knows all the dependencies, it can foresee quicker than a reactive scaler if you don't just need to increase the resources at the front end, but also in the chain down the line, because you understand the propagation of all the cold chains, so you can enact in a single scaling action a lot of changes. Whereas with the reactive scaling, you scale up the front end, then you realize after a few seconds that the back end is the bottleneck, you scale that up, and then maybe there's another layer that you need to scale up. So it takes a lot of steps before you get there. You see this clearly. You see that these reactive autoscalers, they move in steps, right? And so sometimes this can happen also with your predictions. If there is some noise, you're not able to predict as fast as maybe in this initial case where we immediately predict right what we needed to do. And so we went to peak performance. This TPS is performance of throughput for the system. But you see that in all cases, there is anyway an advantage in using a predictive approach. And so sometimes when you do these optimizations, the solutions are a little bit unstable. You change something in a service and suddenly the system wants to reconfigure a lot. And so you can place limits to these, to how much you are allowed to change. And in that case, your behavior can be a little bit less dramatic at times. And so this is a more conservative approach, but it's easy to implement in our research method. So this actually comes to the conclusion of my talk. So we have discussed today a lot, from principles of serverless use cases to concrete open source implementations and more experimental research tools for quality assurance and also for runtime control. This is hopefully something you might be interested to explore further. If that's the case, I would like to point you to the website radonh2020.eu, where you will find all the documents we produce in this project, as well as to pointers to social media like Twitter or YouTube, where you find our videos. And as I shown earlier, we have this Radon methodology repository on our organizational GitHub that gives you pointers to each and every tool. And let me remark this strongly. It is also possible to use the tool in isolation, and so you will find that they are getting started if you just want to use a part of the framework as opposed to using holistically the entire solution. So if you found something potentially of interest among the many tools I've shown, you can also just try that out. So with this, I thank you very much for your attention, and in case there is any question, I'm very happy to answer your questions.
Yeah, I've given everyone the opportunity to unmute themselves if they wish to talk back to us. So feel free. I'm actually very intrigued by these the support for automatic scaling and the automatic load testing, because that's always a big headache.
No, certainly it's one of the features more in demand when we present this solution, because it is difficult to take decisions at times, even to configure this simple auto-scaling mechanism. But if you, with serverless is relatively easy, but with other systems you might need to define the policies, and so you're not sure what to do or how much to wait before take another auto-scaling action. So we try to to use science to help in this.
There are very subtle interactions between Kubernetes pods and the enclosing VM cluster that runs the Kubernetes cluster. So yesterday I was spending all day in a training workshop, and we just played around with minimum and maximum instances, minimum and maximum number of pods, and so forth, and you get very, very surprising effects. So, for example, if you try to scale up to cope with more demand, you find that actually that there may not be enough capacity on the cluster to schedule all of the pods that it wants to schedule.
Oh, I see.
And you end up with a sort of race condition where pods don't start up in time and get restarted by the cluster controller, and you never actually end up come out of this sort of thrashing situation. And it took us quite a while to actually discover what was going on. So any kind of framework that takes those headaches away from you must be really worthwhile.
Yeah, I can understand it can be frustrating, because ultimately, the capacity problem, I mean, in the end, if you exhaust the capacity, there isn't much you can do unless you really provide new resources. It's a hard bound, right? So in software, what we can do, as you've seen from this, is to at least try to tell you if you are getting closer to that bound faster than the moment you find yourself with the kind of problem you have discussed. And I would say perhaps I didn't mention this, but I work in performance actually, so this is really my core research area. And AI and machine learning, as we know, they are bringing a lot of new things also to systems research. And the one fascinating aspect is the speed. Even if simulation now, maybe with these mathematical models, take you milliseconds, if you do that with a neural network, it takes really 1/100th of that. And so we have a generation coming up of new methods to take this decision, which will be way faster and therefore more efficient in searching a good solution.
Okay, we've got a couple of questions. First one was from Tom Gilb, a name you might know. Tom, what would you like to say? Tom, you have the floor.
Yes. Can you hear me?
Yes.
We do.
Okay, good. I started to talk. I'm very interested in non-functional requirements, and you mentioned there was a language for dealing with them. Can you deal with things like privacy, security, usability? What is the range of non-functional requirement?
Thank you for raising this point. So it's a little bit outside the area I work in, and we don't have in the project a strong dimensions on this sense. But what I can tell you is that this modeling language I presented at the beginning, this OASIS TOSCA language, which is also the one that we used to specify this service level assurance policy, as a rich community developing security and policy work, because there is the possibility to define custom policies, and so there are really committees that are looking at how we can annotate these models with, identity management or information roles, access control, etc. So absolutely, there is this dimension. Clearly, in the context of the projects, you need to go maybe more vertical on one particular angle. So we've taken at heart the problem of extending to serverless, the standard in our project. But if I can speak more broadly about the open source that is developed in European projects, research projects, if you search for this Horizon 2020 projects in software engineering, you will find a gazillion projects actually that deal with this kind of extension. So I'm sure we'd end up finding tools also for Tosca and good support.
Thank you.
Thank you. Perhaps, sorry, just one additional point. Of course, the orchestrator in these scenarios would be the entity that configures all the policies and roles for you, right? So the automation arrives there as well, which is available also with the commercial platforms, indeed. But here is portable, right? Because it is expressed in the high-level vendor agnostic model. Thank you.
Thank you again.
Robert Chatley, you have a question.
Let me see.
So I was trying to unmute you at the same time as you were trying to unmute yourself.
Oh, sorry. Is it working now?
Yes.
Okay, great. Thank you, Giuliano, for the talk. Very interesting. I was thinking that the first half of the work that you presented about using the Tosca model and configuring and deploying the serverless application would be very useful for people developing and deploying applications. But would it be right that the things you showed later on about the prediction and the scaling, maybe they're more of interest to the people actually at the cloud provider because they deal with the scaling, maybe more so than the application developer?
Thank you. That's a great discussion point. Yes and no, I would say. Yes, in the sense that from the point of view of the cloud provider, you can see that this kind of controllers might in principle consider end-to-end service management in the situation where you have many tenants that are deploying topologies on a shared infrastructure. So yes, if you essentially synthesize a controller for each platform that reasons on a collection of these models representing your the user of your cloud platform, I can see this being extended to that domain. Certainly interested. The scenario we were considering here is actually a scenario where you perhaps have a on-premise deployment of your application. Say you install OpenFast or OpenWhisk or Docker your organization in private cloud, or maybe you have a hybrid deployment, something in the public cloud, something locally. And so if we are making the proposition here that you are interested to build serverless applications because everything is simple and easy, it's somewhat a little bit inconsistent to say that yes, but the portion of your system that is microservice-based, you have to invent your own management system for the performance. So we felt to reinforce this part with this additional research. And what we are doing is that there are also other initiatives in the project on this scaling bit. This is now being integrated with the Exopera orchestrator. So technically, it will be the orchestrator to issue these commands, which means that you can carry the control at a level of abstraction above, say, Docker or the material platform. Right, so I think it's interesting to see that this is a way to prevent lock-in also for the performance management side of things. Thank you. Great question.
Thank you.
Great. I think we've come to the end of questions, and we've more or less run out of time as well. So well timed. Thank you very much for a very good and fascinating presentation.
Thank you for the invite again. Thank you.
Well, it's very kind of you to do that. If you had a choice of book from the BCS catalogue, then I'm sure that's on its way to you if you've given them an address to send it as a token of our appreciation. So
thank you very much. I really appreciate it.
Remains for me to say a very happy Christmas. May I be the first to wish you a happy Christmas and a very happy New Year. And
likewise.
Let's hope we can go out again by this time next year. I'm hoping that probably before Easter we should be able to resume physical meetings at the BCS. But I'm sure that we'll carry on using this channel to spread those meetings around more widely. We had been using GoToWebinar beforehand in a small way. We typically had 3 or 4 remote attendees at our meetings. I think the ratio will now be much more the other way, where most people will be remote and a few will be physically present. Interesting times ahead, and I look forward to the very next talk. So watch the mailing list and see the invite. Thank you very much and good night. Bye-bye.
Good night. Thank you, Imo.
Always a pleasure, Tom.